Today I'm going to be looking at the PlayStation 2 memory card, how data is stored on it, and the low-level communications with it by the console. This is a deep dive into the memory card, but it is not comprehensive. There are a lot of things still more to cover, and a lot more to learn, but I'm putting this out now to get started on it. I'll have chapter markings or timestamps in the description for various sections of this video. The memory card doesn't have much in the way of components inside it. There is a NAND memory chip, an official or officially licensed cards that is generally made by Samsung or Toshiba, a controller chip which is made by Sony, a clock crystal, and a voltage regulator. The empty pads on this one and the traces seem to match a hex Schmidt trigger inverter chip, which seems to be used in triggering an LED. You can see empty pads for an LED up the top. So there are likely versions of this memory card which have an activity LED inside it. The rest of the components are just resistors or capacitors and a diode. Official memory cards come in 8MB varieties, with some 16MB cards available from officially licensed sources. Third-party and unlicensed memory cards go up to 64 and 128MB. There is even a 256MB card available, but you have to physically switch it between two 128MB banks, so you may as well just call that 128MB maximum. I don't have any of the greater capacity cards yet, but I should soon. Now that we've looked at the physical characteristics of the memory card, let's go into the file system. First, I'm going to go over the file system for the PS2 memory card. I'll be using this page here by Ross Ridge for reference. The link will be on screen in the description. A few words we'll be using to understand the file system are a block and erase block, which is the unit that gets erased on the memory card. Cluster is a middle-sized unit that's made up of 1 or 2 pages. ECC is the error correcting code that will help to correct errors on the memory card if they occur. High half here is a 2-byte value. Page is the smallest unit in the memory card file system, is likened to a sector on a hard drive. Programming is the act of writing to the flash memory. We'll talk about that a bit more later. A word is a 4-byte value. Okay, so the memory card uses flash storage, which is handy because you don't need constant power to maintain the memory like on some memory cards and cartridges like the Game Boy games. It's not as fast as RAM and is even connected on a serial bus, right? So it makes communicating with it a bit slower than some memory cards, but so long as your saves aren't too large, it's not too much of a problem. For flash memory, rather than thinking of the bits as being like a 0 or a 1, it might be easier to think of them as being in an erased or a program state. You can change individual bits from erased state to program state, but you can only change them back to the erased state if you erase an entire block of memory. So if you want to write data to the flash, regardless of how much you want to write, it's best to first make copies of the blocks involved into memory, modify those cached blocks, and then erase the blocks in flash and write those blocks back to the memory in full. Flash does degrade over time. The file system does take this into account by having some spare blocks available, so if blocks go bad, it can replace them. It can free up those spare blocks. Generally, the page size of the PS2 memory cards is 512 bytes, with 16 bytes extra for ECC and some padding. The erase blocks are 16 pages in length, and there are 16,384 pages on a 8MB memory card. The file system itself is pretty similar to the FAT file system, and primarily uses clusters to reference files and data on the card. Usually the clusters are 2 pages in length on the memory cards, which is 1024 bytes of data, and the extra bytes make up 1056 bytes in total for a cluster. The very first page on the memory card, this one up here, is the super block, which gives all the information about the structure of the file system on the card. It starts with a string here of Sony PS2 memory card format, followed by version number. From version 1.2, they have full support for the bad block list. We have the length of a page, which is usually 512. The pages per cluster, which is usually 2, and the pages per block, which is usually 16. There is some variation of these around. I don't have any physical examples, but I have seen them. What's next? The next one is number of clusters per card, right? The total number of clusters on the card, which shows the entire card size. 8,192 on an 8 megabyte card. And then we have alloc offset. This is the first cluster that is allocatable data space. So it usually comes right after the fat table. On an 8 megabyte card, that should be at 41, which is like hex 29 or whatever. We'll see that a bit later. And then we have the alloc end, which is the first cluster after the highest allocatable cluster. So the last allocatable cluster would be 8134, and this 8135 is past, the first one past that. The root directory cluster, this should always be 0. It says must be 0. So I guess essentially this will be where the root directory cluster, or the root directory listing, will start relative to the alloc offset, right? So this should be 0, as it is the first cluster in the allocatable area. But that's okay. Then we have 2 backup blocks. These are used when writing data to the memory card to help ensure that the data is not lost or corrupted during writing. We have this IFC list. That's the list of indirect fat clusters. It is a list. It is not a linked list. It's just a list of clusters. It says here usually there's just one. The examples that I've seen only have one, but technically there could be up to 38 of them. Anyway, there's a bad block list. Again, it goes up to 32, and usually it says -1 here. That means it'll be 0 filled. These are blocks that should not be written to. Apparently the data can still be read out of them, but you don't write to them anymore. Which seems a little bit odd, because if they're bad, the data in them is no longer trustworthy either. So I'm not sure why you'd want to read out of them. Anyway, then we have the card type here, which should be a 2. Show it's a PS2 memory card, and the card flags, which show what sort of, it says physical characteristics, but it's like more things that the card supports. Right, we have in here like the first bit is card supports ECC, or card may have bad blocks, or whether the card sets to erases to all 0s or all 1s. I think usually it is all 1s in PS2 memory cards, but it might just depend on what flash memory they had available. What was available at the time when they were making, certain companies, because not all the cards were made by Sony. The ones that I have actually are not made by Sony at all. I've got ones that are made by Fuji, and when one or two they're made by Hori. So it could have just been what suppliers that they picked, which types of NAND they got, where they erased to 1s or 0s. For our purposes, it doesn't really matter, because when you write data to it, the controller takes care of that. So what else have we got here? Things like they've got some things here. Things like page length, pages per cluster, pages per block seem to be fairly limited in their values of like 512 or 1024 for the page length. The pages per cluster is either 1 or 2. 16 pages per block seems to be the usual, but you can't assume that. I've seen one example of a 32 page per block memory card. My assumption is that this was high density NAND. So the NAND went up in density, which made the blocks, each block sort of larger. And so you end up with more pages per block and smaller NAND chips. But yeah, so you have to be more careful of that. If you're making code, writing code for dealing with a memory card, you're going to have to be careful either to support all sort of geometries, or make sure you reject memory cards that are not supported by your code, or else you can end up corrupting memory cards. Of course, it seems to be fairly easy to recover memory cards, so long as you have a way of wiping them fully. You can stick them back into a PlayStation 2 and reformat them. But if it's just corrupted, often it's quite hard to deal with unless you've got a way of wiping them, like completely wiping them. So yeah, be careful. There doesn't seem to be a limit on the number of clusters that you can have, really. So if you have a maxed out IFC list with 32 clusters, you can have up to apparently up to 8,388,608 allocatable clusters, which would be like 8 gigabytes. I do not think any such memory card was made, but it would be interesting to try make one, I suppose. But anyway, let's go have a look at this on a real memory card then, shall we? Okay, so this is a full dump of one of the memory cards I have. I only have 8 megabyte memory cards, so they're pretty standard. But I do have a 64 meg virtual memory card that we can have a look at a bit later as well. You can see that the Sony PS2 memory card format string up the top here, right? And the version number at the start of the card. This one is the version 1.1 actually, so it does not have the full bad block list support. This means that it actually has more allocatable clusters. If you see here, over here, on the end of the allocatable clusters is 8176, whereas on the version 2, which I have over here as well, I have to drag this all the way to the top. On the version 2 one here, we have 8135, right? So the total number of clusters on the memory card is the same, but with the 1.1 format, it is not reserving clusters for replacing bad blocks. So to be clear, there's nothing different about the hardware on the memory cards at all. It's just a version of the file system that was written to the memory card when it was formatted. So the V1.1 format card must have been formatted on an older console, older firmware software on the console that wrote an older format file system to the card. It would work the same on all consoles, except that if a bad block is found, it won't extend the allocatable space to reclaim that space that has become unusable. The bad block will just be added to the list and is no longer used, and you'll lose a little bit of your allocatable area, your free space on the memory card. We'll go back to the super block here. You can see that this card has 512 for the page size, 2 pages per cluster, and 16 pages per block. There are 8,192 clusters in total, and the first allocatable cluster is cluster 41, which would be page 82 if you're keeping track. The 2 backup blocks are at 1023 and 1022, as expected. Looking at the indirect fact table list, there's one entry at number 8, which means that cluster 8 is the only cluster making up the indirect fact table. The rest are all filled with zeros. Interestingly, this will be the first cluster. Cluster 8 will be the first cluster of the second block on the memory card. I think this is likely done to remove the need to erase the first block and thus the super block during normal memory card operations. It's not exactly dangerous, so long as it's written back correctly. But it would reduce wear on the super block compared to other blocks on the card, making it less likely to go bad until the rest of the card is well degraded already. But thinking about it, that block, that card that has the 32-page block size, if it has the indirect fat in the 8th cluster, that would still be within the first block. So I wonder if that's still in the same place or whether it's moved on that memory card. I kind of want to get my hands on one now. Back to this, we have the bad block list here, which is all filled with FFs, showing there are no bad blocks listed in here. And then we have the card version, which is card type 2, and the supported features on here. If we look, the first bit here is set, so it's got ECC support, and the 4th bit is set, so it may have bad blocks. Doesn't seem like it's got any, but oh well. And bit 5 is not set, so the erased bits will be 1. As we can kind of see here, these are all 1s, right? This is all 1s. So yeah, it erases to 1s. The rest of the values in here, I do not know. I could hazard some sort of guess at them, but if we're looking at like how these are spaced out, this is probably 1024. But for what reason, I'm not too sure. This here would be for 256, again, don't know why. But then you have 2 bits here, and that would make this one here 8. And again, I don't know why. That would be like that. And then we have an FF sort of ending blocking point here or something. Interestingly though, this value here, this half value, comes to 8001. Now if I look at this, the 64-bit, the 64 megabyte card, virtual card here, this one comes down to 65,000, which is pretty close to 64,000. And I even looked at the 32 megabyte memory card, and it came to 32,001. So it could be roughly setting up the size of the memory card, just an easy reference, but I'm still not too sure what it is really. The values after the card flags in the FAT table are the cluster size, the in bytes, the FAT entries per cluster, clusters per block, this one for card form, and the root cluster there, and the max allocatable clusters. But that's basically all of the super block apart from these CRC bytes here. We might go over those a little bit more later. That's kind of fun. Anyway, let's go have a look at the indirect FAT table. Okay, so here we are at the indirect FAT table. This is just a list of sectors that make up the FAT table, right? A list of sectors, well, it points to the sectors that make up the FAT table. So the FAT table starts at sector 9 and has sector 10, 11, 12, 13, all the way down to sector 40. Right, and of course it goes down to 40 because sector 41 was the start of the allocatable area, so which is the sector afterwards. Right, so you have these sectors here, and you can see that most of this indirect FAT table, this sector is, or this cluster is empty. Right. And actually, again, if we have a look at the 64 megabyte card, 64 megabyte card takes up the entirety of these two, of this cluster, these 2 pages, for the indirect FAT table. So the maximum, I guess you'd say, unless in this geometry, the maximum size memory card you can have with a single indirect FAT table cluster is 64 megabytes. Right, so that's a fairly long one there. So, yep, that's empty there. And then the next is the beginning of the next cluster, is the beginning of the FAT table itself. This is cluster number 9. Again, if we look at the 6 megabyte card, there's nothing on this memory card, but the first cluster is allocated. So the fact table is a form of linked list with each entry being 4 bytes and either pointing to the next entry in the directory listing or file data, or the end of the listing, or the end of the listing or file data. Right. Each entry in the table relates to the cluster in the allocatable area starting at position 0. So this is position 0 here. This is cluster 0 in the allocatable area. This is the root directory cluster. Right. If the top bit is set, so the top bit comes up with 80 over here, right? That top bit there is set. Then the cluster is in use. Otherwise, it is clear, or it is available to be used. We look at the first entry in this table. This is for cluster 0. We can see that it is in use. The top bit is set. And the next cluster in the listing is cluster 1. Right? So if we look then at cluster 1 here, we see it is in use. And the next in the listing is cluster B7, or cluster 183. Right? So if we go down to where B7 is, this one here, because we've got the B6 is there, which would be B5. That would be B6, I think. B7, B5, B6, B7. I think it's this one here. Be the next one. We can see that the next one in this listing would then be 15B, and that would be cluster 347. Right, and so it goes on and on. Right, we can see a few entries here are all Fs. Those show that that's the end of a directory listing or a file. If we scroll down a bit over here, we can see that there are a bunch of ones that have the bit and top bit not set. So those are ones that have been deleted files or deleted directories, which haven't actually been removed. They've just had those top bits removed, so that you can allocate them again. It does mean that if you could write software that would recover those files and directories if you wanted, but I'm not going to do that. And then we have these ones here that are all Fs except for the top one, which is 7F, which shows that they have not been allocated, they have not been written to, they are in their default state that they were formatted to. And we can see in the 64 megabyte card that is empty. The very first cluster is used by the root directory, but all the rest are not used because it's all Fs. The top bit is set. Okay then, so let's now have a look at how the directories and files are laid out on the memory card. Okay, so the directory entry on the file system is 512 bytes, which means that if you have 2 pages per cluster, you can have 2 entries per cluster. The file data itself uses all of the clusters that it is assigned to, so you won't have 2 files occupying the same cluster even if they are small enough that you could, right? There'll always be one file gets assigned to one cluster. The directory entry has only a few elements in it, really. It has a mode, which identifies what type of file is and what sort of flags are there. It sets the type permissions, whether it's hidden. Down, where's the hidden one? Down, yep, where it's hidden. Whether you can enter it from these sort of permissions over here. And also whether it exists, right? This top bit shows whether it is existing or in use. I actually use both of these 2 bits here, the second to top bit and the top bit, in combination to identify an active directory or file, because a completely empty area in, because this is in your allocated allocation area. If it's completely unset area, it'll be FF. It'll be all FFs. So the top bit will be set, and so if you're trying to identify whether you've got a directory entry here and that top bit is set, then you just check for that. Then you think it's already something, right? But when you actually when you actually have an entry, the top bit will be set and the second to top bit will be a 0. So you can use those two bits together to check if you actually have a file or directory entry in this page, in your directory listing. The next thing we've got in our entry is the length, which is a word, a 4-byte word, which is the length of bytes if it's a file, or number of entries if it is a directory. We have a creation time. We have this one here, cluster. It's the first cluster of the file or the directory list. It says here that in dot entries, this is the first cluster of this directory's entry, parent directory instead. I'm not sure if that's exactly true. The second one here is only used in dot entries, the parent's directory. It might be supposed to be dot entries instead of dot entries. Anyway, then we have the modification time there as well. It's 8 bytes, and we have this attributes, user-defined attribute. I've not seen used. That's all right. And then we have the name, which is the name of the directory or file. That goes up to 32 bytes. It's supposed to be 0 terminated. So make sure, well, don't trust it. Make sure you only read up to 32 bytes, or write only up to 32 bytes. And yeah, but you should make sure you 0 terminate them. All right. So there's one thing to be careful here. They sort of mention in here that the modified time never changes, but in the root directory, the modified time does change. That's something you should be careful of. You write the modified time whenever you write a new save or make a save or delete a save on the memory card, because you also have to update the number of, or the length of that root directory. We'll have a look at that in a second. Otherwise, the dates are stored with a byte for everything, 1 byte for seconds, minutes, hours, day of the month, and this is not a word, it's actually a half for the year, 2 bytes for the year. That takes up 8 bytes, with actually there's one unused byte at the beginning. That's all right there. And there are some illegal characters that you're not allowed to use as well. All right. Okay, so let's have a look at how this works on the memory card. Okay, so here we are looking at the root directory listing on the memory card. We have one entry here and a second entry here that makes up cluster number 0. Right, start 0 indexed. That's fine. So you've got this directory listing, 8427, fairly regular, standard for directory entries. It shows that this listing has 9 entries in it, in this directory. We have a creation date here, which has 14 seconds, 17 minutes, 14 hours, so 2:17 p.m. on the 9th of the 12th December 2005. So quite a long time ago. Really? 20 years. The memory card's doing pretty well. Both of these ones here, the cluster and directory thing, are 0, and then we have a modified date on here as well, which is 45 seconds, 47 minutes, 21, so 9:47 p.m. on the 13th of March 2020. So, hey, this memory card used for a good 15 years. Good on them. User attribute is empty. And the file name is just a dot. It's pretty hard to see over here on this side. Hard to make out against the other dots, the grey dots on here, but yeah, it's just the dot directory. The second one is a bit unusual. It has this A426 mode, which means that it's hidden and you can't read the directory. It's probably because under normal file systems, the dot directory is a way to go up, and so they want you to not be able to go up from this directory. It has no length. The modified time is the creation time is the same as that one there, and is unmodified, right? And we have that name of dot on there. That's all right. So the next one, we have the first directory in the root directory. Another unusual one with AO27, right? So this one is also a hidden one, and it has 5 entries inside it. We'll just sort of ignore the modified times again. This is 2006. Last modified in 2020. Right, that's right. And it starts, right, this directory starts from cluster 2. So right now we are in cluster number 1, right? This was cluster 0 for the root directory. This one here is cluster 1. So this directory's listing starts in cluster number 2. And it is called B data system. So some sort of system data. And the second entry that's inside this cluster has a normal listing. So it is visible, it exists, it's a directory, it has 5 entries inside it, and it starts from cluster 7. Its directory listing starts from cluster 7, and it is a save file for some game. I don't know what game that relates to, but that's right. Right, so that's the end of cluster 1, and so we go into cluster number 2, and you can see that we have another sort of root file system here, right? We have another dot directory. We are in cluster number 2. It points to itself. And this one here is zeros for the dot directory. See, I'm not sure entirely. This one is now actually visible and executable. So, I mean, I get the feeling that this is a way to go up, right? When navigating your directories. But because you usually don't have subdirectories inside subdirectories, it probably doesn't have, it doesn't ever change from being zeros here, because the only place you'd go up to is the root directory again. So it's always just zeros anyway. So this is cluster number 2, and we go into cluster number 3, and we have our first file that we've come across, right? So cluster number 3 here, we've got 8497, which is a file. It has a length of 462 bytes, the day created. This file starts at cluster number 4. So the file data, in this case, starts at cluster number 4. Modified time, and the name of the file is history. So some kind of system history. We have a second file in this listing, in this cluster. It is a file size of 1776 bytes. And this file starts at cluster number 5. And it's called icon.sys. Icon.sys is the default sort of file used on the PlayStation 2 that tells the browser what icon to use for the save file. Then, seeing this is cluster number 3, cluster number 4 starting here is the contents of this file. Right, and it was, what was it again? 462 bytes. We go down to here. We can see it is 462 bytes of data, and the rest of the cluster is not used. Right? No other files can be put in there. That cluster has been assigned to the history file, and that's all that can be put into it. But it's also just a single cluster is assigned to this file. So that's cluster number 4, and cluster number 5 is the start of the icon.sys. All right, and that's just how it keeps going on and on through the file system. So let's go back and have a look at the fact table again to talk about how we find all the clusters that make up a file. If you remember the history file from before, it was in cluster number 4 and only took up one cluster, right? So remember that these cluster entries are in this table are 0 indexed and point to the next cluster in the directory listing or file, or indicate the end of a file or end of a directory listing. If we look at the index for cluster number 4, so we start here with 0, 1, 2, 3, 4, we see that it's all Fs. The top bit is set, which means it is in use, right? But it is the file is only a single cluster in length, and so this does not link to any more clusters. It is the end of the file. Right. However, the next file, the icon.sys, that starts at cluster number 5 here, right? And it was 1,776 bytes in length. So it goes beyond one cluster, and we can see that this cluster is linked to cluster number 6. So if we go look at cluster number 6, which is this one here, it is all FFs, right? And so that's the end of, that shows the end of that file. It is all Fs or -1. If you look at this as a signed integer, it is -1. So that's another way to think about it. Sorry, that one there. Right. So it's the last cluster in that file. Right. Otherwise, it will then point to the next cluster that makes up the file. Right. For example, that would be a bad example here. Maybe this one here that starts at OA, right? And goes to B, C, D, E, and then end up down here where it's FF. So that's probably one big file there, right? One big contiguous file. So seeing each cluster that each cluster index points to the next cluster that makes up a file or directory listing, you can use the table along with like the directory listing to find all of the next clusters that are making up the file or directory index that you are wanting to navigate. Right. This does mean that the clusters that make up a file can be fragmented all across the memory card, depending on what clusters are free at the time that you're creating the file. But it's fairly unlikely that you'll get large amounts of fragmentation. Some of the files are very small, like see these files like history and icon.sys are fairly small. They're often fairly small. When you get to this down here, we've got like 3 clusters in a row that are all FF. Usually like this is the end of a file or something, or end of a directory listing, and then you have like the icon.sys, right? Just takes up one cluster, and then you might have another one that just takes up one cluster in the middle there, and then you go back into like another file. That sort of thing happens sometimes, right? You'll see it. You will see this sort of thing quite often in the file system once you've, right? There's another one down here. There's another one over here, right? These are basically like the end of a directory listing and the icon.sys and maybe one other file. It just happens quite often in the memory card. Yeah. But you end up with quite a few like quite contiguous files in the memory card. And this one here must be quite a large file, really. Probably goes all the way to here. But anyway, so that's basically how the FAT file system works and how data gets laid out across the memory card. Alright, so lastly, there are a few more things to cover. So let's go back to the web page. Okay, the last things to cover, we have the ECC values. We find them at the end of each page. They take up 12 bytes with 3 bytes for every 128 bits of data, 128 bytes of data on the page, and 4 padding bytes. You can see example code for calculating these bytes here. And in the PS2 SDK, you find almost the exact same code in the PS2 SDK. I've used this code and it does work. It is valid. You can use the code in the SDK if you want. Either way works. You have to use this table though. Alright, this is the magic table that works. That's fine. The 2 backup blocks, they're used when writing to the memory card. The normal process is to erase both the backup blocks first, and then write the data that you'll be writing to the memory card into backup block 1, and the target address that you'll be writing to in backup block number 2 at the start of it, right? And then you write your data, then you erase the block that you'll be writing to, and you program it, you write your data to that block, and then you erase backup block 2, right? And that sort of indicates that you did your write operation successfully, right? If that block is not erased, when you insert the card into PlayStation 2, it may think that there was a failure at writing that final block, and it will take the data that was in block 1, and it will write it to the address that was left in block 2 and then erase block 2, right? Just to try to fix that mistake. So you have to be aware of that to do it properly, or else you might end up overwriting something accidentally. Make sure you clean up after yourself. But strictly speaking, you don't have to follow this this process. Right, the memory card won't care. You can write directly to blocks. Well, you have to erase the blocks first, but you can erase a block and write directly to it without using the backup blocks. It will allow you to do it. The only problem is that if there is it's a little bit more risky than using the backup block system to sort of ensure that you had successful writes. One interesting thing is that the final backup block 1, will retain that block that was written to the memory card. So if we go back and have a look at this memory card, we can see here this is the last block that was written to the memory card. Let's scroll down, right? The last sort of 8,448 bytes, that's one block. You can see with the 7F here, these FF7F, that this is the last part of the FAT table, the final part of the FAT table. And we have our root directory listing here, sector 0 in the allocated area. And sector 1, sector 2, sector 3, we have the history file is in here, and the icon.sys is in here, right? So that was the last block that was written to this memory card. Alright, so that's about it for the file system itself. Next we'll have a look at communications with the memory card, low-level communications. In order to understand low-level communications with the memory card, first you have to understand the SIO2 interface. Unfortunately, no one really fully understands the SIO2, but we know enough to serve our purposes here. The SIO2 interface is mainly in charge of communications with the controllers and memory cards. Most of this is relevant to controllers as well, with a few differences, but if you come to understand memory card communications, you should also understand the controller communications by just looking at my control subroutines. There are only a handful of registers you need to deal with in the SIO2. In the order listed here, we have send 3, send 1 and send 2, the FIFO in and FIFO out, control, receive 1, receive 2, receive 3, and istat. Of these, the receive 2, receive 3, and istat don't really need to be touched. The control register configures the SIO2, it triggers sending the commands, activates send or receive modes and directionality. It says here that the value is set to 3BC on reset, but you may find it set to 3B0 on your console. It also says here that to send, you'll set the value, logical or the value with 1, and then write it to control to trigger the send. And that may work for code that is running on the IOP. But if you want to trigger this from the EE, you need to logical or the value with 3 instead, so that bits 0 and 1 are set to 1. Otherwise, the command will not actually be sent to the controller or memory card, and the interrupt from the SIO2 will trigger immediately. Send 1 and send 2 are a series of registers that alternate for each port. So you have port 0 send 1, then port 0 send 2, then port 1 send 1, port 1 send 2, up to port 3. So this is 8 registers total, each 4 bytes wide. These appear to configure the interface for communicating with the devices on the ports. Controllers use different values for these than memory cards, and you can lift these values from your console if you read the values from the registers and dump them from memory, because during boot up the console, BIOS will set these values based on what you have connected to the console. Send3 is an array of 16 SIO2 commands. Now, all the time I just use single commands, and that's fine for me. But allegedly, if you want to read both controllers, you could put both commands and send them at the same time. The first 2 bits are the port number, and for this you have 0 or 1 for the controller ports, or 2 or 3 for the memory cards. The other 2 values here are listed as fake command length and real command length, but in other places they're also called send length and receive length. So far I've not seen any commands that have different length for send and receive, so anyway they should be the same values shifted into these positions. So a command length of 9 would be shifted 8 positions to the left, and also shifted 18 positions to the left. The FIFO in and FIFO out registers are 1 byte shift registers. It's possible to set up DMA transfers to move data in and out of these registers asynchronously, so you can continue to run other routines while the transfers take place. But you can also, from the EE, just read and write continuously to these registers to move commands in and out and get replies out. I've not tried it, but I assume that if you set multiple commands in the send3 register, then you just write in the multiple command packets in a row into the FIFO in, and it will cut up that list of bytes based on the command lengths you put in the send3. So this would let you queue up a bunch of commands, send it off to the ports, then go off, do something else, and come back when the interrupt fires, which I assume will be once all of the commands have finished and returned. One thing you need to be careful of is to clear out the FIFO out register after a command, or you may end up with data being offset when you come and send the next command. So you need to keep track of how much data you're expecting back and read that out. The last important register here is receive 1. While it states here that it indicates the peripheral is connected, it may be better to think of this as reporting a response from the peripheral. The response is usually hex 1100, and if there is no response or the device or no device connected, you get hex 1D100 or something else. Now I say it's more like a response from the peripheral because memory cards that are not authed will have hex 1D100 in receive 1 after normal access commands, even though it is connected to the console. In this way, receive 1 can be used more like a did the command I sent work kind of a check. One last thing we want to look at is the IOP interrupts. If we enable the SIO2 interrupt on IQ17, then this interrupt will be raised after starting an SIO2 command once the reply is received. For controllers, this usually takes around 1000 instructions on the EE to get a response back, which is pretty quick, but it it may be worth doing other work while waiting for an interrupt to be raised. And of course, you can enable these interrupts from the EE. Nothing I'm talking about will require running any code on the IOP. Alright, so we've gone over the SIO2 interface registers. Now let's look at the commands we have for communicating with the memory cards. Remember, most of the format applies to controllers as well, but they have different commands. In general, add one more byte to each of these commands in this list. You can refer to the PS2 SDK McMahon module over here for these command links as well. Alright, so command hex 11 is a probe command. Personally, I don't see much use for this command. The idea seems to be to check if the memory card is there, but it doesn't return any useful data, and seeing any command will return 1D100 or 1100 if the card is able to be accessed. You can just use any command for this purpose, and some of them will give you some useful data back. 12, hex command 12, seems to be a confirmation or a flush after doing an erase in particular. Checking if an erase operation is complete. It returns 066 as a terminator while the erase is busy, and the set terminator value once it is complete. Hex commands 21, 22, and 23 are respectively used to set the page where you will do these operations. For erase, that page should be the start of an address block, but it seems that any page address within blocks should work for deleting the block. For reading and writing, that page could be anywhere. These functionally set a pointer on the memory card where you will start reading or writing, and it will automatically move that pointer along. Hex command 26 is get specs. You get a summary of the memory card geometry, which is a command that I consider more useful than probe. Unfortunately, it doesn't return the number of pages per cluster, but I think that's more of the superblock information anyway. Hex commands 27 and 28 are set and get the terminator value. This is the value that is the final byte returned by the memory card after each command. Why exactly this is useful, I'm not sure. Perhaps they wanted to prevent a kind of hot swapping of memory card, or at least give the ability to detect it. Hex 42 and 43 are for reading and writing data to the memory card. They are large commands, each having space to send or receive 128 bytes. This means you need to use 5 in order to read or write an entire 528 byte page, including the ECC bytes. You can set the length you want to the read or write command, but in general I'll avoid doing that for reading data, especially if you want to continuously read data from the memory card, as you can easily mess up where the pointer is. When reading from the memory card, you can continuously read up to a block boundary, which is also divisible by 128. So my process is to almost always read out the entire blocks at a time, the exception being the super block, and you can only continuously write data up to a page boundary, which means that you'd write 120 bytes 4 times, and then 16 bytes for the ECC data. Hex 81 is used when you finish reading or writing a contiguous section on the memory card, likely a page for writing, and it may have something to do with checking the ECC bytes of the page written, but I'm not sure about that. For reading, you can use this command once you have finished reading an entire block. Sort of once you're done reading a section, you're like, right, free up that pointer or whatever. Hex 82 is the most dangerous one. This erases a data block on the memory card that you addressed with Hex 21. It just completely wipes it. From what I've seen, this command will return before the operation is finished taking place. So you need to wait after each erase command. From what I've seen, the average time for the erase is about 2 milliseconds. It might vary a bit from memory card to memory card, depending on the actual NAND memory that is in the card. But I think the ones that I have are fairly old, and they're about 2 milliseconds for the erase time. It's fairly easy to set up timers on the PS2 to either count that out. It could even give you an interrupt so that you can do other things and then wait for the interrupt to fire. But you can also wait for a V-blank, which is about 16 milliseconds at 60 Hertz. The memory card is still communicative during this delay, so you can't just check for 1D100 results or anything like that to wait it out. You actually have to use a timer in some form. If you try to send a command after erase and the card is not ready, the command is generally ignored. I say this for especially writing. The commands like get specs will return the actual data, but if you're writing, that'll be ignored. That's particularly bad because you can skip into writing entire pages. Imagine writing back the fat table with pages missing. Ask me how I know. And I don't use BF1 at all. It doesn't seem to be really documented either here or in the PS2 SDK, so we'll just ignore it. Alright, so until now, these commands work only if the memory card is authed. If the memory card is not authed, sending these commands will return a 1D100 and receive 1. There are 3 commands related to doing authing on the memory card. For starters, we'll start with our F3. This is a kind of auth reset. This is sent first before starting the auth process. In a way, this can be used to detect an unauthed memory card because it will result in hex 1100 message and receive 1. However, it will reset the auth status of a memory card that is already authed. So unless you are paranoid about whether the card is still legitimately present, you should check if you can communicate with the card normally before using this command. The next command is hex F7, which seems to be a key generation command, telling the card to generate keys that will be required to send to the Mechacon during the auth process. Hex command F0 is the last, and it's the most common, it's the most used command. And it actually has a whole bunch of subcommands, and is the only command that I know of that has a variable length. The first byte following F0 is essentially a counter for steps through the auth process, starting at 0 and working its way up to hex 14. If an error occurs at any point during this auth process, such as an incorrectly handled key exchange, the command response will have a terminator of hex 66, and also any subsequent auth messages will have 1D100 in their receive 1 until the command F3 is sent again. So either way, it can be used to detect an auth failure. The data that is handled in the F0 messages is usually 8 bytes with a 1 byte CRC. That is just an XOR of the 8 data bytes, and needs to be reversed in order before being handed to the Mechacon. The same with messages that come back from the Mechacon. This will be shown in the code later on. So that mostly covers memory card related commands issued over SIO2. Now that you know these commands, you too can write code for communicating with the memory cards. Of course, looking at some code may be more helpful before diving into coding your own functions or low-level routines, so let's get on to that. The first place to start when looking at writing memory card code would be at the MICMAN module in the PS2 SDK. It seems to be strongly based on the XMCMan module found in the PS2 BIOS, and it likely has all the major features support you need and could modify or build on. If you're looking to just write simple game save and load functions, you could easily reduce the amount of functions and code required. And if you're not worried about compatibility, or you just want to make use of the memory card port for a kind of expansion port and utilize the SIO2 interface to communicate across it, you do whatever you want. The sky is the limit there. Just do anything. There are a lot of interesting features in the MICMAN module, but we're not really here to look at the C code. We want to have a look at the really low level stuff. So let's go have a look at my assembly routines. Now I'll preface this by saying that these routines are not complete. I already have ideas for improving these routines by adding more functionality as well as more tools. They have limited card geometry support and feature support, so I won't go dumping them into programs. And I'm going to be spending months and months on these. So, I mean, I want to release this video at some point, so that's why I'm just making this now. At the heart of memory card communications is the main SIO2 comms routine. So in here, memory card com. I actually have two similar routines, one specifically for getting the card specs, because I store that in a separate position in memory, and this other one I use for all the other memory card communications. Seeing they're basically the same, we'll just look at the get specs one for now. In this case, I actually have a retry set up to try 5 times if it doesn't get a positive return from the command. Which is a hex command 1100 in receive 1, which see down here, right? So we start off by setting up the SIO2, not deleting things, right? We do this, set it to idle, then the default value, which was hex 3BC, or maybe even check your console to see what that is. Usually, then we set up the values for S1 and S2. In this case, I'm setting up the values for both ports 2 and 3, which are the 2 memory card slots, slot 1 and 2. I'm strictly using memory card 2 for all my functions for now. Memory card 1 is always framework boot for me, so I don't want to touch that. I think later on when I want to make memory card dumping or memory card cloning, I'll have to use 1 as well, but we'll get there when we get there. These values that we have in here are specifically for the memory cards. Go up here, you can see I've got different values in this for using the controllers. That's fine. So yeah, again, these ones here you can dump from the console if you have controllers, memory cards plugged in. When you boot a program, yeah, you can dump these values out. You read them and dump them out. So next we want to set up Sen3, which is this one here. So we get the length of the get specs, which I'll have to show. You can see the length of get specs on screen now, and I'll show this other times as well. So we get that length of the get specs, and we put it into this register here, into S3, and we shift it across 10 spaces, right? Shift it left 10 spaces, and then we OR that value in again, and we shift another 8 spaces, so the length is shift 18 and 8, which are the 2 correct positions for it. We do need to have this 40 hex. It turns out this is required to set up the transfer mode. It can be another value. It can be like hex 60, I think works as well. It's not too clear what the differences are, but it can't be 0. Anyway, and then we also set up the port value here, which port we are referencing. 0 for controller 1, 1 for controller 2, 2 for MC memory card 1, 3 for memory card 2, and then we store that into the register here in Sen3. Okay, so the next we want to write the command into the FIFO in register 1 byte at a time. This is the same subroutine I use for the controller. I store this length of the command into the stack, so I'm going to use it again later. And so I will just have a quick look at that routine. Here he is. Here's our FIFO in write. Just a quick sort of loop. We load the bytes out and store them into the FIFO, which will just shift them all in. Then we come back. So yeah, it just loads the bytes one at a time and writes them into the register and returns. And then we do our SIO interrupt. We we clear it, we make sure the interrupt is clear, right? Make sure it's clear, and do that, and then we can start the SIO2 transfer with this by ORing the value in SIO2 control, which will be this idle value. We OR it with 3 and write that, because you need the bottom 2 bits set to start the transfer, which is the thing I found out. And once we start that, we wait for the interrupt to fire. Now, right now, I don't have a timeout on my SIO interrupt wait, which is bad, because if it fails to return for some reason, you'll just get stuck in this loop. But I'll fix it up some other time. So, yep, we just wait in this loop until the interrupt comes back, and then we can read our response out from the FIFO. I load into the address where I want to save the response to, and then call this FIFO readout, which is very similar to the read in one. FIFO in write, FIFO out read, right? And then in MC specs, we're going to have our result sitting there. Then we also going to check receive 1 to see what our result there was. As long as receive 1 is 1100 hex, then we can return, otherwise it will loop through here again. So if we look at the COM routine, it's essentially the same, except that we're using a different memory location here, the MC scratch, which is just an area that I use to mostly buffer stuff in and out for the reading and writing. But otherwise, it's essentially the same. Also, S0 comes in with the command location in this case, instead of having that hardwired command like we did in the get specs. So you'll load S0 with the address of the command that you're going to use, the command list that I have at the bottom, included at the bottom, and then you call this memory card com, or another memory card location where you've built a command that you want to send to the memory card. We'll see some examples of that later as well. And then you call this command, and it uses that. Many of the other commands are customizable in some ways, so I usually build them in memory before calling this routine, but static commands can be directly referenced. This is done with the set command routine, which I've got down here somewhere. Yep, here we are. Right, which again, I take the pointer to the command, S0 is the pointer to the command, which I use to make, which I could make a tighter loop that restores S0 before it returns, but I'm dumb. That's alright. I'll fix this up some other time. It's fine. Everything's fine. There's some other helper routines. This set address is used for the read, write, and erase commands, where we have to set an address on the flash memory where we want to do the operation. So you either write, erase. We set that address, and then we can call the memory card with the COM routine. We can send this to the memory card with the COM routine. We've got an end read write command. Where did I put that? I think it's down here. There we are. End RW, which you call after reads or writes before you start doing other operations. Or you do it at the read or write boundaries. Read boundaries are erase block aligned, and write ones are page aligned. Or so it seems. We've got some other helpers in here. We've got one here for erasing blocks. I have the address must be erase block aligned. That's not entirely true. It looks like if you address any page inside an erase block, it will erase the entire block. But I think it would still be better just to align it with the blocks. Have a routine here for reading blocks, reading pages out of the block, out of the memory card, writing pages. I do have a thing here for writing a block, but this one is redundant, or should I say defunct, because you can't write beyond a page boundary without ending the write and readdressing. So I need to either remove this or rewrite it so it does the writes page at a time. They're also, I mean, these routines also have hard limits to 528 byte page sizes, so they need to be improved to support more card geometries. But that's fine. The rest of my standard memory card handling resolves around this memory card find page routine, which will return the address of a cached memory card page. And if the page has not been cached yet, it will read and cache the block that contains that page into memory. So again, it's not geometry agnostic, so it needs to be upgraded, but that's fine. Everything's fine. If it is caching a block, it will call the cache block routine. This one here, right, which will load up the memory card using a start address. Right, let's set a start address. Empty buffer will start reading the block into memory. It'll store the entire block into the cached area and add the block address to the current list of blocks that are cached, which is got this thing, sort of these things here, block cache P and block cache, or whatever you want to call it. As a helper routine to this, this one here, got this cache dirty routine, which keeps track of which blocks have been modified to only write back modified blocks when you get to writing back to the memory card. Which we have this cache write back routine here. So the cache write back routine, when you call it, will go through that list of dirty blocks, build pages with their CRCs into a buffer. So you've got this thing down here making CRCs. It's not great, but it's fine. Which is, again, not geometry or feature agnostic. Things need to be done. It's fine. And then it'll call the write block a routine down here yep, there we are, write block. That's write block, not block write, or write block, not write underscore block. I don't know what it was before. Some of my naming needs to be redone, perhaps. And that routine, which is over here, will go through the process of erasing backup blocks, the erase 2, and erase. Did I erase one? Don't think we erased one. Oh, we erased one down here. Right. Rewrite the block that we're going to write to it. Anyway, it'll go through the process of erasing the backup blocks, writing the backup blocks, writing the data block, and erasing the second data block finally at the end for each block that you're writing back to the memory card. Now, I'm not going to go through the routines for actually reading and writing the file system on the memory card in detail, because there is quite a lot going on here. In short, you'll need to cache the fat table so you can traverse it and look for existing files or free space for your save data. You'll need routines to look for particular directories or file names while traversing those directories. I think here we are, search directory. This is the one I got. Right. And once you've determined target sectors that you're looking for, got some fine space here. Once you've determined those, like where you're going to be saving to, then you'll need to have, like, I'll check names here as well. In this one here, save data routines for actually writing to those sectors and building the target directory listings and updating the root file system and all of that. There's quite a bit of stuff in here. Slowly built up over time. And I need to go back through it and improve it. That's fine. So one more thing I want to show, and that is this routine for getting the current time from the real-time clock on the PS2, which you would use to set the created and modified times on the PS2 memory card file system. These use the CD registers. I'm seeing the param byte to EE, but I don't think it's actually necessary. Anyway, you send this 8 hex command byte to the S command register, and then you wait for this little wait loop thing here to get a response back. So I read the bytes out one at a time. The bytes come back in binary coded decimal. The first byte is a space. So I think, anyway, the first one is a space. I skipped the fourth one because I want to cut that in. That's right. So you get a space, then you get the seconds, the minutes, the hours, respectively, and then another space a byte, and 3 bytes for day, month, and year. In each byte, each nibble, each 4 bits represents a digit in the value, meaning that only 2 digits for the year 2000 is implied. That could mean that years above 2099 can't be represented. If your PS2 is still working in the year 2100, please post in the comments what year your console thinks it is and what year new saves show up as. Because I want the dates in format for the PS2 memory card, I do a conversion from binary code decimal to the memory card format here. But I might want to save both of them because I'm going to need, I think I might need the binary coded decimal for another project, but we'll cross that bridge when we get there. Binary coded decimal is kind of annoying. You have to sort of split up the 2 parts, the 2 nibbles, and then do some conversion from that binary into, no, I should be right. No, wait, because it's yeah, because it's just binary in the PS2 memory card, a binary representation for values. So you have to actually convert it from the binary code decimal into binary, which is, yeah, just a little bit annoying. Just end up adding a bunch of lines here if we have to save it. It's fine. Everything's fine. Go and add 2000 to it. Alright. So that's it for the standard mode communications for reading and writing into the memory card. The final part of this I want to go over is the memory card auth process. Firstly, I'm going to do an overview of the auth process. Every communication has a send and receive aspect, so the arrows are going to represent a kind of data direction. Some responses actually give data back, and some commands actually carry data. So we start off by sending an auth reset command to the memory card. This will change the memory card mode into auth mode, and these standard access commands will no longer work. Then you send what I'm calling an auth reset to the mechacon. Then you select the key that you want to register to the memory card. I think 1 and 3 are available keys on the retail memory cards, and the most common is on these scads 1 is used. Then you send an auth start message to the memory card and one to the Mechicon, and this starts the auth dance. So from now on, all the commands have like incrementing ID bytes. That's fine. Next, we want to read two 8-byte values from the memory card. These are called memory card IV or memory card 4, and memory card material in the PS2 SDK. And then we send these two values to the Mechicon. And then we generate one more, or we load one more value from the memory card called memory card nonce, and we send that to the Mechicon as well. There's something of a wait or verify with the Mechicon, and you need to write back. Here's the wait. Yep, the prepares, and then you have to read back 3 8-byte values from the Mechicon, which were called challenges, and it comes back in like the first challenge, and then half of the second challenge, then the second half of the second challenge, and the third challenge. So I use two reads to get those 3 back. So then we send these. We send challenge 3 first to the memory card, and then we send challenge 2 to the memory card. And then there are these 3 commands sent to the memory card, which are somewhat, unknown, which I think they are either testing or generating things on the memory card and preparing for the next values that it needs to receive. In here, if there is a problem with the challenges, like you've got the wrong challenge bytes in the wrong order or they're invalid, you'll start getting error messages, an error value back. And then we send the challenge 1 to the controller, and it has another 3 afterwards as well, which may be also generating the next response. We start reading these. If everything's gone fine, we start reading these responses from the memory card, which are also 8 bytes in length. So get response 1, and the next command may be generating response 2. Then we get response 2 from the memory card. We send both of those to the Mechicon. Then perhaps the next command is generating response 3. We read response 3, and we send response 3 to the Mechicon. Right, so now we've got all those responses sent to the Mechicon. There's another wait or verify sort of thing that goes on with Mechicon now. And then finally, we send one final message to the memory card and one final message to the Mechicon, and everything is done. At this point, the memory card should be back into its standard mode, and you'll be able to do standard communications with it, assuming there are no errors along the way. I have not actually checked to see what happened if you have an error at the very end on like the Mechicon or the memory card. I'm assuming that the auth mode, the auth complete, when that is sent, assuming there were no errors, will actually switch it into the standard mode. But I have not actually tested that yet. Now the way that I have it implemented is essentially the same as the PS2 SDK, but I will quickly go through it. Okay, so I have 3 helper routines for the auth process. One for the Mechicon communications, and it's very similar to the RTC routine. It also has some space set aside to hold input and output data. And I do have a to-do sitting somewhere around here. Yep, because I'm not actually testing if there's errors occurring. That's fine. It's okay. Everything works. The 2 other routines I have for reading data from and writing data to the memory card. You need to reverse the bytes that you read from the memory card before you send them to the Mechacon, and the bytes that you get from the Mechacon before you send them to the memory card, and that's why I have these weird offsets and subtractions for the writing bytes here. That's fine. In the auth write, you also have to calculate a CRC, which is just XORing all the bytes, the contents of all the bytes together to make a single byte. That's a CRC byte. That's fine. I do have a mistake here about this one here, calling this routine once all the 8 bytes are in MC command to generate the MC. That's wrong. It should just be, this one here will put those bytes into MC command and generate the CRC and put it in there, but that's fine. I should get rid of it, but it's fine. Anyway, let's go to the actual auth process. So we start with an auth reset here, right? We load this auth reset command. I might be showing on screen what that command looks like. And we send that to the memory card using set command to write it in there, and then using that to send it to COM. I guess I could really just, because auth reset is a set sort of length, I could get rid of this and just send that straight to command to the COM. It's fine, who cares? And then we write into Mecha input the CNUM for memory card 2, which is 9. I think for slot 1 it would be a 1, hex 1. I'm not too sure. I haven't tested it yet. It's on my list of things to do. We put it into the Mecha input, and then we send that to hex 80 to the Mechacon auth routine. Right, so we send that one byte of data to the Mechacon, which tells us that we're setting up memory card 2. Right, and then we load this auth key, which I should be showing on screen again as well. We want to register, and we send that to the memory card. Right, and then we send the first auth byte, which will be a 00 byte to the memory card starting the auth process, and we do 81 to the Mechacon, which starts the auth process there as well. We're reusing that CNUM that was put in input at that time there as well. Right, we're using the CNUM from before. So then we're loading out card IV or card 4 from using this auth read write. So we read that out, and it's being put into the Mecha input. Right, and then we read the material, and we're putting it into the Mecha input as well, offset of 8. Right, we're just shoving along a little bit, and then this routine will send 16 bytes from auth input to the Mechacon on SIO2. So then this one here of hex 3, the auth routine as well, probably generates the next value, nonce, and then we read out nonce into the auth input, into Mecha input, and we send that to the Mechacon 83 with a length of 8. So it's just the one value, right? And then we have to send one more number 5 to the memory card, and then we do this weirdo F8 or 8F, sorry, which is like a wait or a verify or something to the Mechacon, and then we're going to start reading back the auth challenges. So we send 84, and then I've got to move around some of this data that these bytes that come back from the Mechacon, just because you get half of the second challenge in the first and then half in the second. I've got to rearrange those around a bit in memory. That's fine. I take a double there from 0 and put in then offset 24, then from 8 and put into 16. And then I have to use words for the rest of it. So it just gets offset a bit. Reload this one here the second time. Right, so reload those 3 challenges back. It says here the challenge 1 should be in plus 24, 2 in plus 16, and 3 in plus 8 now. And we send challenge 3 first. Alright. And because it has to be reversed, I have this offset of 15 here, and it will read them through backwards as it's going auth right. It will read 8 bytes in reverse from 15. It's weird, I know, who cares? So we're sending these to the memory card. Right, all 6 we're sending challenge 3 to the memory card. All 7 we're sending challenge 2. And then we've got these 3 8, 9, and A, which are probably, like, if they're invalid, you'll start getting error from one of these commands. And you'll also start getting 1D100 in the receive 1. So you can use that in here to check if one of those failed. Because once, let's say you got an error back on this one here, the error would come back with 1100. But when you try to do the next one, it'll give you a 1D100. So the 1D100 check can tell you if you've received an error beforehand. And that's fine. Assuming you get through these fine, you can go for the challenge 1 using B. And you send that challenge 1 to the memory card. You have these 3 again. Right. I feel like this one here is probably generating response 1. But I'm not too sure on that, I guess. Anyway, F will be reading back response 1 from the memory card. 10 could be generating response 2. In 11 we read that back and we put these into mecha input, right? Then we send the first 2 to the mechacon, response 1 and 2. Using 86 and a length of 16. We send those to the mechacon. 12 could be generating response 3. Here we read response 3 from the memory card using 13. And then we send that to the mechacon with a length of 8. So it's just the 1. And we've got another 8F here, which could be the final test. And assuming that passes, 14 is the final command sent to the memory card, which probably converts it into that standard mode. And then we've also got 88 sent to the mechacon, which finalizes that one as well. So at this point, memory card communication should be as normal. I do want to redo this whole process and add in error handling and streamline it if I can, but that's going to be for a later date. The final thing I want to talk about is an overview of the memory card auth and access. It sort of goes like this. First, you probe the memory card to see if you have access. You can do that probe with the probe command or get specs, whatever. If you get a 1100 result, you can access the memory card and do memory card actions like read, write, and erase. Everything's working normally. If not, then next you will try the key reset command. If you get an 1100 result, the memory card is present and you can start the auth process. And once that completes, you have memory card access. You can do memory card actions, right? If not, there is no memory card present, or there's some other error occurring, like bad communications, corrupting communications, anything like that. And you should just show an error that there's inability to access the memory card. So that's it. We're at the end of this deep dive into the PlayStation 2 memory card. There are a lot of things I know about that I haven't put into this video because I'm still learning more details and I still have a lot more to learn. I may make a second part at some point, but I'm not committed to it. If you made it this far and found it interesting or useful, I hope you'll try out some of my other videos, and I hope that you'll be back for the next video, whatever it's about.